And today I'm really happy, and I must say, to have my team here and to present this project. And for another reason also, this is my hometown. Having so many experts in wood, I'm proud. Okay, READiStrength project. The subtitle tells the aim and also what it is about. Resource efficient, data-driven, integrated log and board strength grading. I will have the short introduction, and the introduction will be in 3 parts. This is the first part. Short about the partners. In Sweden, from above, we have my university, Wood Science of Engineering, and then we have at KG Sawmill, Norra Timber, the industrial partner. We have RISE all over Sweden, and the unit here in Skellefteå, and the other places in Sweden, at the Research Institute of Sweden, RISE. And in Germany, we have FVA, Forest Research Institute, Baden-Württemberg. And in Austria, we have HFA, Halsforschung Austria. And they are all been contributed very strongly in the project. Some words about the background and the motive for the project. We have talked about it during the days. The demand increases on the wood resource, and the wood resource is limited. So there is a severe competition for raw material on the market, actually. We have also different uses of wood. We have new products coming out from the forest, wood fibers. So it's a pressure in general. So that is some kind of background motive. We have also the climate change. This is a little bit threat I'm talking about now. The climate change causes, we see that in Europe, a pressure on the popular one product species, spruce, Norwegian spruce. So it's insects attacking, and we have then the situation that many forest owners, they also replace when replacing with new other species. So that goes in line to look for other species for bendings, for strength graded timber. So we may have less raw material available for the construction timber industry. That gives us a motive that we need to do the production very efficiently. On the other side, at the sawmilling side, and how to produce it, we see it's more and more popular. We need very good description of the material. We see also that almost all products going to the construction timber industry, that is strength graded required. And all in the area, we would like to produce it as efficient as possible, of course. But something not new, but growing year by year. We have been better and better in characterizing and measuring already at the log level with new modern techniques that we will use in our project. You will see that. So we will have data very early in the process when producing plank and boards. And as I said, the branch, we may need to look for alternative species also. So that is important. Our approach, we have looked through the arena of strength graded production of such products that we will hear Anders talk later on a little bit of different scenarios, how to do this to make it more efficient. That it should suit different sizes of companies. And our bearing idea is to strength grade early in the process. And with aid of such techniques as 3D scanning, acoustic scanning, discrete X-ray already at log level, and computed tomography. So our main idea is can we already at log level predict the outcome of the boards coming out from that log, the strengths of the sawn timber. In that way, we think we can save material. Just something about our data collection. It's a huge data collection. You don't need to understand this, but we started from the very beginning with logs, marking, and so on, and followed the production chain through the sawmill, of course, far away, even to the final product, and then strength tested it. And we made it in a way that we could keep the full traceability, that we knew that exactly this board is coming from that log, and that log has got that facilities, and that board has got these features suitable or unsuitable for the strength-gated timber. Just to get a grip, we had in total 420 logs followed on 2 continents. No, not continents, but up in Scandinavia and Central Europe, divided. In all, we had 1,200 boards. We had a similar distribution on 4 species. Of course, we had Norwegian spruce, the popular one, but also Scots pine, Douglas fir, and silver fir. To make it realize this, it was a lot of logistics. So running through sawmills, as you see, 6 sawmills and 5 labs. What we did measure through the process was at this level, and I'm not going to go through the details here because we have such presentations later. So both on the log level and the board level, and then this strength testing. In Central Europe, we had tension strengths, and up in Scandinavia, we had bending strength tests due to practice on our market, so to speak, how we did according to practice. We also did interviews with the scanner deliverers companies and also with sawmills about their thoughts about future, and that is compromised in 2 reports at RISE. Recommend to read. What is coming next? Yeah, we will have the industrial perspective on strength grading in next presentation. We will hear something about the implementation. Hopefully you will understand what we are thinking of doing here. We will hear something about the forest owners, how can they benefit of this? But in the second part of our project presentation, we go a little bit deeper and present also the prediction result and our attempts to show that if it's possible or not. Yeah. Then I give the floor, actually it's a recorded presentation by our industrial partner, Johan Oja. I hope it will work if I press on the...
Hello, my name is Johan Oja. I work as a technical manager at Norra Timber, the industrial part of Norra Skog, the Forest Owner Association in northern Sweden. I also work part-time as associate professor at LTU. Today I will talk about READiStrength, industrial need for more efficient production of sawn wood for structural applications. And even though I'm not able to participate at the conference today, I'm glad to have the opportunity to give this presentation in this way instead. So the background for this project is the need for raw material efficiency. We have an increasing use of wood in the building industry, and we want this to increase even more to exchange concrete constructions to wood constructions. But we also have a limited amount of wood, and that means that we have to use the wood as efficient as possible, of course. The problem when we want to utilize wood in an efficient way is that wood is, as you know, a biological material. That is, we have a huge variation of properties. Every log, every tree is unique, and thereby we have to find the best way of utilizing every single log. But today, the fact is that we are actually not using wood to its full potential. Most construction wood is sold as a strength for 24 megapascal, C24. That means that when we use the wood, we design as the wood having a strength of 24 megapascal. But if we look at the random boards, so the strength distribution of random boards from Norra Timber Säva sawmill, as an example of a typical sawmill in Sweden, we can see that we have the average strength is about twice that strength, around between 45 and 50 megapascal. And that means that we are actually not using wood at all to its full potential. And if we want to use wood more efficiently, then we need to define the strength better. That means we have to find better ways of defining the strength. To do this, we need better measurement technology, and that is what we have studied in the READiStrength project. We need to look into the log if we want to have the exact information, as accurate information as possible. But of course, we could also look just on the outside and try to predict what's inside the log. But if we're able to look into the log or predict what's inside the log, then we can make a decision on how to utilize the log before it's actually sawn. And the example of how we can make money from this is that we can look at the potential dimensions that we can cut from the same log. We say that we're able to cut dimension A and B. They are both geometrical feasible for this size of a log. But if we cut dimension A, the customers want high strength material. They want to dry it to low moisture content, and they can pay a really high price if they get this value. But if it's a reject, if the board doesn't have this high strength, then we have dried it to low moisture content, and we don't have a customer don't have a demand for this dimension with low strength. For these logs, it would have been better to cut dimension B, because here we have a standard quality that fits most of the boards in this log class. We can dry it to normal moisture content, and we get a decent price. And for the reject, we get less price, but we still have some demand for the reject. So that means that what we would like to do in the sawmill is to find the logs that will produce the high strength and cut dimension A and dry it to low moisture content. And the other logs we would cut dimension B and produce standard and reject. This would give us the best value. And this would be in a typical situation where we have 50%, we would cut 50% dimension A, 50% dimension B. You can see from the dimension A, we get 2/5 of high strength, and the rest 3/5 of reject. And for the standard B, the dimension B, we have 4/5 of standard and 1/5 of reject. This means that we get, even though 40% of the total values has high strength, we only get 20% out as high strength lumber. But if we're able to choose the perfectly choose the high strength logs, we can find these logs, which is 40% of the total amount of logs. We strength grade those logs and able to cut dimension A. And then we will produce only high strength value for these. So we get 40% instead of 20% of the total material as high strength, high value material. And the rest of the material, 60%, is cut to dimension B, where we produce 48% of the total flow will become standard instead of 40 as before, and 10% is the normal reject in dimension B. In a total, this will give a much higher value with no of the lowest value, the reject with dimension A, and a high amount of high strength lumber in dimension A, giving us a much better value, much better utilization of the logs. And this is what we would have tried to achieve with the READiStrength project. Thank you.
And that explains pretty well, I think, that if we can really look through and use that information already at the log level and predict the strengths, then we can save material. And now I try to have some small dialogue with my experts here in the sofa. Anders Lycken from RISE, where are we now concerning these strategies, these different sawing strategies and sort grading strategies? I know that we have worked with it, and you will try to explain a little, because it's not that easy for newcomers.
Yes, I'll try to explain very briefly how strength grading is done today and how it might be done in the future. You can see here that traditional strength grading, you pre-grade the logs according to length and diameter, and then you saw the logs into boards. You have a green sorting where you sort again to diameters or dimensions. You dry it, and you have the final sorter where you do the actual strength grading. And then, as Johan said, you have a lot of rejects, but that's how it's done. What we want to do is to have it log strength grading. The problem with that, just in this case, is you can apply the strength for all boards according to the lowest grade of the log. And that is not too good. By that, you miss a lot of high-grade boards too. But if you could trace the boards within the sawmill, then you can put different grades to the different boards and still keep track of them. And that's one way to do it. Or you can have this sequential strength grading when you on each phase enrich and take away the rejects so you don't process them too much. And that's one way to do it. Or you can say it's 4 ways to do it, depending on how much money you have, how much money you want to get to put in the log strength grading, how much you can buy scanners for, and so on. So, and we try to do it in the 3rd way here, with long strength grading, with tracing of boards. So we have just one strength grading.
Thank you very much, Anders, because this reflects also the different scenarios dependent on the size and technique they have at the sawmills. You can give the mic to Rune Sitén at RISE. You're Mr. Standard and Mr. Strength Grading in Sweden, I would say. You're the expert on strength grading. What are the requirements so that log strength grading can work in practice?
The overall requirement on structural materials, whether it's wood or something else, is that 95% of the material shall fulfill the strength requirement for the grade. And that is including all type of errors when you reach that. So for grading today, when you do the grading on the sawn plank, the main errors are lack of correlation between the property measured by the grading machine, the indicating property, and the basic properties of the board, such as strength, stiffness, and density. The other main source of errors is errors in the machine readings of the material. If we move the decision of the grading to the log, we will add new steps to this process. There will be errors in the model, and there will be errors in the traceability between the logs and also within, in some cases, within the log. That means that when the total sum of errors are the same, but you divide it into more steps. And that means that you can accept less errors in each of the steps, and thus you need to have more restrictive, more conservative limits for the settings in the grading machine, and this can also lead to a lower yield of the material.
How big is this kind of disadvantage, could you say?
It depends. It depends on the quality of the source that you grade, and it depends on the quality, the grade that you want to have. If you have a very high yield, the effect is quite low. If all the boards fulfill the requirements, you don't need a traceability because it will be okay anyway. And then the lower the yield is, the more effect you have from lack of traceability.
Mm-hmm. Thank you very much.
Sorry, I just want to add that this is an effect when you do the final decision of the grade on the log. If you add a second step where you grade the plank as well, then this is only some kind of process optimization, and it's not reflected in the settings. However, you change the source material, and you need to determine other settings for the material.
Mm-hmm. Thank you that we had a lesson here. Mm. Okay, Udo Sauter, FVA, Freiburg, Germany. Until now, we have looked upon the sawmilling industry, but the raw material comes from the forest. Udo, what are the benefits of high-tech log quality assessment from a forestry point of view? Can you picture that?
Yeah, thank you for this question. I prepared some few remarks to that from my point of view, and the hope is, of course, that the achieved added value from the wood industries will be shared with the forest owners who are delivering the resource, of course. And this is very important that this will functioning at the end. And second remark is that forest owner could be motivated by doing so to produce even trees and logs of higher quality by adapting information coming backwards to their silvicultural treatments. And this will at the end fulfill the expectations and demands from both sides, and especially from the wood industry and related to the end users, of course. And overall, this will strengthen the competitive position of the stakeholders, the involved enterprises, as well as construction timber as such, because this is underlining the expression that we squeeze out as much as possible out of our resource. And I have to come to some few more aspects which is related to the supply chain. It is very important that the quality related to or the quality which is included in the data, this has to flow upwards and backwards, which means we have to fulfill the need and developing solutions on the point that from the forest stand, the data information can flow before felling already to the sawmill, and after processing a log or several logs, we have to make clear that this information can also flow backwards, that this information can be used from the forest owner side. Mm-hmm. And the last thing, it's especially for me, with a long experience in that, very important. From my point of view, it is very important and necessary to implement kind of neutral resource quality determination after felling, but before sawing the log. And I'm reflecting to the system which is already established here in Sweden. You are lucky guys, and this is not the solution already in Middle Europe, and we have to implement such a system. And the reason is pretty easy. Otherwise, we cannot really expect that the forest owners will react as we expected.
Thank you, Udo. So to summarize, if the sawmill is doing it better, more efficiently, they earn more money and they can pay the forest owners. They can then pay the forest owners. And that was not a question.
Sure.
Just a comment. Yeah. Andreas, Weidenhiller, HFA in Austria, Vienna. You led the Austrian part of the READiStrength. These options and talkings that I have just been discussed, are they also interested for you in Austria? What is the situation there?
Yes, definitely also these options and scenarios are interesting for Austria. I don't know if every one of you is familiar with the fact that Austria, despite being a rather small country, is one of the biggest producers of sawn timber in the EU, together with Sweden, Germany, France. It's something that's really relevant to Austria as well. One thing that I noticed during this project that may be an interesting fact is I observed that the cross sections that are sawn in Scandinavia are somewhat smaller than the cross sections that are used also in Central Europe. So Germany, Austria, we had much larger logs in the project, not totally representative, but still interesting. So a lot of more boards in one single piece of log, which exacerbates the challenges of traceability. So I guess that for Austria, for Central Europe, the last scenario of those shown here, the sequential strength grading, is probably most interesting, also in line with what Rune said before.
Okay, thank you. Back to Rune, I had an extra question to you. Talking about these standards, Rune, what does strength grading standards say about log grading? are there any possibilities to use that technique? Because I got a little bit uncertain listening to you. Do the standard allow log pre-grading? That is the question.
Well, that actually become two questions.
Okay.
But if we start with pre-grading, then we often say that pre-grading is not allowed, and it's not false, but it's only partly true. What the standard really says is that the material that you use to determine settings must be representative for the source that you use in production grading. And until today, all settings for the machines had been determined on ungraded falling sources, and therefore they cannot be used for pre-graded materials because they are no longer representative.
And these settings, are they complicated to get these?
No, I would say we haven't done it yet, so there might be different opinions about it, but as I see it, we add all the time new geographical sources to the existing settings, and a pre-graded source is just another source in the same way as a new geographical source. And then there are, in the standard, there are very precisely described the procedure to do it. So it would be quite easy.
Thank you. Like poo, then we can continue and hope for this, our idea will hold. Thank you very much, guys. And then we will have a change getting into the next section of our project. Yes, tackar. And leaving the floor to Franka Brüchert from FVA, Freiburg, Germany. And you look over here, I think. Let's see. We are waiting for the presentation.
Thanks very much. So let's put some flesh to the bones. So it was a little bit of theory, and now a few slides on the technology that we used and on, say, really very initial results, really. Have in mind, so this is really a pilot study on ideas that had been developed on grading logs prior to sowing. So we actually used 3 technologies. The first one, and I would say technologies, but concepts of measurement technology. So the first one, very widely used in the sawmilling world, is 3D log scanning. So the idea is that the log runs through a frame. We have either a light curtain or we have laser cameras, and from these measurements we extract a point cloud describing the outer shape of the log, and from that we can extract variables like length, diameter variation, extract from that taper, ovaliness, bumpiness. So it's the outer shape as such which is described. And having that that shape, that geometry, we can then put the boards in there and draw relations to the strength measurements that we've done on the board. So each board I'm talking about had been destructively tested, and tested also for density and for MOE. So the second technology, which is more used over here in Scandinavia, and it's not that, I don't actually know of any installation in Central Europe, is discrete X-ray log scanning. So again, the log runs through a frame, and we have 1 or 2 X-ray sources installed, and what we receive from this technology are kind of silhouettes for each of those two sources, we receive one of those two-dimensional representations. And from that data, again, we can extract, say, the geometry of the outer shape, but we also receive information on the wood density levels. And so wood density is very closely related to strength. So the information that we gain here is already very important, because we do see some patterns already in distribution of density. So we can extract hardwood diameter, for instance, or the position of walls or knots and their sizes. If we then go further into technology, so that is the most advanced technology that we were able to use, and there are about 10 to 12 installations worldwide of that technology. And so we are lucky to have one here in a sawmill, and in Freiburg we used, say, a prototype which is actually the basis, or a little bit of the basis of these industrial installations. So the difference to the to other X-ray based technology is that we have an X-ray source which actually travels around the object while the log is moving, and the result from that is not only one or two planes which we are looking at, but we are able to look at several hundreds individual planes, which are then recalculated to a proper 3D representation of the log internal structure, as you can see here in the cross-section or in the axial length. And from this, again, we can extract, again, all the external data. We can extract the wood density level in much more detail, as I've shown in the image before that. So we can find the actual precise position of knot structures. We have information on the status of knots. So the detailness of information is higher than with the previous X-ray based technology. So we collected a lot of individual parameters from each of those three technologies. And in Sweden, statistical approaches based on partially square analysis have been applied. In Germany, Austria, we used a different approach, so it was generalized linear models for the modeling. All the data sets have been split up, as you would do when you build models and training data sets and test data sets, 10 replications. And I would like to present you now just the model qualities which we can achieve from the different technology concepts. And so that's the example for Norway spruce. And what we have here is from the left to the right, we have, where is the pointer? From the left, so it's 3D X-ray scanning. That's a combination of 3D and X-ray and the CT. And as you see here, so this point cloud between observed and predicted seems still pretty fluffy, pretty, I wouldn't say weak relation for the models. And when we add some information or more information in particular on the density, so that point clouds, they kind of orientate and say they become denser, and they become, say, the relations become more clear. So that was the example for Norway spruce. And now we are looking into the 4 different species that we have tested, and I start with the most, I would say, difficult one, which is silver fir. So that was really XXL logs, top size between 45 to 75 centimeters. So it's really huge logs, and some of you might be familiar on silver fir. So in these dimensions, it's very prone to wet core. So that means with, say, the X-ray technology, the density you measure that contains a lot of water. So, and we have with these big logs a lot of individual boards. And so what you see here is, say, only by using the outer shape of the logs, we have a very low R square for predicting the individual board strength. If we use X-ray scanning, so that actually increases by a factor 2, it's not as brilliant really with an R-square of about 0.3. But still, say that's huge logs with a lot of individual boards predicted. So, and with CT scan, we aim at a precision of R-squares to 0.5. And now coming to the other 3 species, we see different but slightly better results when looking at Douglas fir. And now that's the concept. For these 2 Central European species, we modeled the individual boards because there were so many boards and we expected a lot of variation. So our colleagues in Scandinavia, so we have for all of those 3 technologies, we have this increasing trend. But if you're looking at Norway spruce and at Scots pine, we are pretty good with 0.7 to 0.75 R-squares, which means that is a really good prediction of the board strength. For these 2 species, I would say, because they are small, there are only 2 boards, so the approach was to look at the average and the mean strength of the 2 boards coming from 1 log, so you can also play with that. So, and just to let you know, again, have in mind that is a pilot study, and altogether we used 420 logs. We're about 1,200 boards, which is overall for 4 species a very small number. And I would hand over to my colleague, to Magnus, for the rest what we've done.
Yeah, thank you, Franka. Now we are moving on to the other end of the sawmill after sawing, and when we have the actual boards. My name is Magnus Fredriksson, very Scandinavian name. I'm from Luleå University of Technology, working here in Skellefteå with Olof. And as we said in the beginning here, this is where the strength grading usually takes place, where we have the sawn boards, and in our case also the dried boards taking place. And we don't want to talk too much about how it's done today, because that's not very interesting from a research perspective, but we will talk a little bit about the technologies being used, since this is where we have based our data collection on. It's these type of scanners. One type is you use camera board scanning to run the boards through a frame with cameras on top and below, usually. And you have projected laser lines, so you can do laser triangulation and measure the shape of the boards, and the cameras pick up the RGB channels, so you have basically a picture of the board. And I'm not sure how visible it is here, but if you do in this way, that you project laser points in a line, you can also measure the fiber direction of the board. Because the laser light will propagate in the fiber direction, so you will get kind of elliptical laser dots, and you can measure the shape and the direction of these ellipses, and you can tell something about the fiber direction, which is of course very important for the strength. So a few things that can be measured. There are a lot more characteristics, of course. Not all of these are relevant for the strength as well, but these are some of the examples. I mean, knots and the fiber direction, I would say, is the most important things here when it comes to like camera board scanning. You can also do this stress wave scanning, where you use kind of a hammer to knock on the side of the board. Most of you know this. So you can measure an eigenfrequency of the vibration, and if you also know the density of the board and the length. You can measure these in some other way. You can measure the length quite easily with a laser scanner, for instance, and for the density you could use scales and measure the volume, or you could use an X-ray. Then you have sort of a function deciding the modulus of elasticity of this board. And we also have X-ray technologies on the board side. For instance, we don't have an image of this, but you can of course scan the board as well to get X-ray data describing the density and the knot information and so on. So that's already known technology, so to speak. It's in use in many places and so on. So what we wanted to do is look at what is coming now in the sawmill. What is kind of the forefront of technology, and we described it a little bit in the beginning of this presentation. If we can have traceability and actually combine technologies from different parts of the sawmill, because the difficulty in a sawmill is often that the pieces and the material, it gets jumbled about, it gets sorted, it gets resorted and so on for various reasons. Especially for the drying, you have to basically resort the material to have an efficient drying process. So it's very difficult at this stage. Let's see, where is it? Wrong button, sorry. At this stage, where you have the board, it's very difficult to know which log it came from. Because you can't really keep track of the pieces. But what is being used in a couple of sawmills at the moment and being installed in more and more, it's coming there. It's this fingerprint traceability technology where you, if you have an X-ray scanner for the logs, you can measure and see these sort of vertical darker areas which correspond to the knot whorls in the log. And you can use this to create kind of a fingerprint, a biological fingerprint of the log. And you actually measure basically the same thing on the boards later. You measure the knots again, and you can create a similar fingerprint, and you can match this to retrieve the information from this at the board stage. And we wanted to see what we could do with this, and the idea was if we can feed forward the information from the log side, when we do the prediction on the board side, can we improve it? That's the question. And it turns out that we probably can. This is one example for Norway spruce, as Franca showed previously, an observed predicted plot. This is not the output of the actual industrial system, I should mention that. It's just a model based on the camera scanning. So this contains quite little information actually concerning the strength. You don't have the density, you don't have the fiber direction and so on. So it's, as you can see here, this cloud is quite spread out, and it's kind of a weak model. But if we think that we can trace the board back to the log and add the log information, because then we have taper, for instance, and we have things like that indicates the log type, if it's a butt log or a mid log or a top log, or we have other things. In this case, we also add the density from the X-ray scanner. Then we can see quite a large improvement in this case in this cloud. So in this case, we have added the X-ray and 3D data from the logs. And we can also have a look at the different species as we did for the log scanning. This is the same whisker plots as you saw previously from Franca. But if we add board scanning, we can see that we have a bit higher R² for the silver fir. This is pure board scanning, and if we also add log data, we can get an even higher result. And we see a similar pattern for most of the other species, actually. There are some differences. You shouldn't really compare the different species to each other, because these two on the left side from Central Europe, there were a bit differences in how you measure the strength and so on, and also the actual scanning systems used both for the log and board side. But the main takeaway, I would say, in this case is that you can have actually an improvement if you supplement the board data with log data. You get a better prediction of the strength. Yes, so that was our takeaway from this, and then I would like to invite Johannes maybe to thank you to do the next part.
Hi, I'm Johannes. I'm an associate senior lecturer at Luleå University of Technology over there in Skellefteå, and I'm waiting for my presentation. Yes. I was told to entertain your tired minds in this one of the last presentations, so please bear with me. Which is very easy to do if you have CT data, in fact. And I was going to talk about using X-ray computed tomography data, so it's the one you know from the hospital, right? To generate finite element models of virtual timber and then predict certain properties. So this is what we envision in a perfect scenario here. We have a sawmill process, very simplified. The log comes in, we scan it, we saw it, we dry it, and so on, and then we do some grading. And nowadays, this grading is based on pretty much statistical models, statistical correlations to predict certain mechanical properties. My vision is to use the plentiful data we gather in these X-ray CT scans, add some computational mechanics to it, and produce numerical models that could predict certain properties of the planks to improve our grading and maybe one day even say a target use for that specific plank we're looking at. The main question in this project has been, how do we get from CT data to a numerical model? I have not read anything about that. And the thing is, why do we do that? We want to predict, at least in Sweden where I work, the bending behavior of the board or a plank. The data we have collected has been a subset of the data you've seen before, where we did log scanning, board scanning, and at the scanners, some of you that you have seen in our facilities at LTU, the gathered data consisted basically of density images. We also did some eigenfrequency measurements with hammers on the planks. And then we subjected them to the 4-point bending tests, where we measured stiffness, strength, and also a crack initiation, a location of initial crack initiation, at least an estimate that we could see. We didn't have any high-speed cameras, but we could estimate it from the observations in the lab. What I've mostly worked with during these projects is to generate finite element models of planks, scanned planks, where I reconstructed the pith, the anno rings, the knots, and the fiber deviations around the knots, made a finite element model out of it, and did the bending test. Lately, and it's actually not really part of the project anymore, I've also progressed into doing the same thing for logs, for the log data before cutting, or for sawing. And that's what I'm going to show you today, because I think it's most fun. Where I reconstruct the knots again, the fiber deviations, and did some models in Abacus to predict. So let me take you on that journey, how I work here. First, we start off with CT data. So that is voxelized data. You know all what a pixel is. A voxel is a 3D pixel, if you want so. In this case, we have voxel sizes of approximately 0.68 times 0.68, and then it's been interpolated to be 0.68 in the third dimension as well. We start off with this cube, really. I remove the air. The blue one has been air, low density, just by segmentation, and we have a image of the log. You can see the high density in red, the low density in blue. You see an initial problem already here. There is a lot of water in the sapwood there, which will obstruct our views in later steps. But I have found a very simple procedure by a thresholding method called OTSO for certain parts of the histogram to just filter away the sapwood and look only at the hardwood, where we can see the different features much clearer. I calculate the pith, or I reconstruct rather, the pith from the data by something called the Huff transform. It's an image analysis tool where you look basically for concentric circles and then follow along the log. And you see the green line here then is approximate the location of the pith. It's good enough for my uses. The next thing are of course the knots. We need to know where they are. They are the biggest problem, obstructing the fibers and so on. What I do there is I do an initial thresholding of the data, so the high density is mostly knots and other disturbances. And I then go along and for each single object there, I calculate the principal axis of inertia, and I take the lowest. So that means I take the axis along which you would most easily rotate these objects around. And then I see where do these axes actually go, and where do they come closest to the pith, which would be the yellow points there. And according to some criteria, I then say, well, this is probably a knot, or this is not a knot. For example, this pitch pocket up there is probably, or it's actually water up there. It's not a knot. It's too parallel to the pith. I'm then left with these colorful objects here, the knots, which I have identified. And then I extend them out into the sapwood. And I do that because we don't see anything in the depth, or we see something, but it's really hard to discern different features in the sapwood because of the water. I use elliptic cones here and elliptic cylinders to shoot off into the sapwood. You can see it looks like this in the end. They come to the very surface as well. The next step is then to go into around the knots, or actually in the entire continuum. I will show you this for this knot group here. We color them red for easier visibility. And I use an image analysis tool called the gradient structure tensor, from which I use the lowest eigenvalue and see what's the eigenvector for that to give me the deviations around the knots. And this gradient structure tensor is based on the derivatives in each spatial direction of the density with some smoothing on it, but that's details. And what it gives me is the longitudinal direction of this coordinate system I'm trying to find, right? I can show you some pictures. It flows around the knots. If we look inside the knots, it also follows the direction of the knots. We can look at it in a little bit higher resolution if you want so, and fly around and see, okay, looks okay. They deviate around the knots. And if you do some corrections and do everything correctly, you can actually plot some streamlines around them and see how the directions flow around the knot and dive into the knot from below and from above. Then you need to assume certain interaction between these directions in the knot and also among the knots with specific laws that have been, that I take some of them from a colleague that sits here, Markus Lukaczewicz, for which did similar models for surface-based data of boards. I then go along and do the same thing for the slices to figure out the remaining two directions that I need for my fiber coordinate system. Now, ignore the areas around the knots, but look at the clear wood, and you see that you can easily find the radial direction pointing inwards towards the pith, the back lines here, and the tangential direction. And now I have all the directions in there, and I go ahead and cut out virtual planks from the logs. And we can see that all the information that I have now reconstructed can be overlaid here quite easily. You see the knots and the pith and the fiber deviation around that knot group. What's then done is I have basically a continuum description of the fiber coordinate system. I call it a tensor field F here. And I take that for every material point, take it out. So it's this coordinate system. I put on an orthotropic stiffness law that we are aware of, that we usually use for modeling wood in a continuum. So it's an orthotropic stiffness tensor here that is based on the following law that has worked for me. It's a power law based on a certain reference stiffness tensor from the books. A factor kappa telling me if I'm inside or outside a knot, And the relationship of the measured density to a certain reference density up to a power P, which in this case was 2. And for the board models, I also used just to check what happens if I factor in the measurement of the eigenfrequency. So the hard part is over, then you do the discretization into a finite element mesh, and I do some refinement around the areas of the nodes, because there I expect the stress gradient to be largest, and I expect the most interesting part of the simulations. Then I do a virtual bending test and can do different things with the results. For example, just measure the deflection to get an idea about the stiffness, or look at the longitudinal strain along that board, slice it up into certain pieces and do a regression on these slices to get a law how the stiffness varies along this board, which is the red one there, and if you do some smoothing, it equalizes out a little bit. But you can clearly see that it drops in certain direction, in certain locations, which is simply around the knots, right? Then I can also do some crack initiation, or I mean, at least I can predict where is the most likely position a crack would open. I don't do the calculations afterwards, how it really propagates. For example, I use the maximum stress law across the fiber, or I used also to try a multi-Saiwu surface. I also did some simplifications of this to see how they work. For example, one-dimensional finite elements models derived from the bigger ones, and also continuum models, where I simply reduce all the information about the stiffness tensor in every point to a uniaxial stiffness along the board, which gives me another continuum representation of this E zeta here, which you see it falls down around the knots, and then do just some projections to get again this stiffness profile, but now derived from the uniaxial stiffness in the continuum. So I basically have 3 different models here to predict different things in the reality. What I can roughly say, because it's not based on a lot of different measured planks, it's I think 20 planks in this case of Norway spruce. It's possible to do it, number one, and number two, the finite elements models were the most successful to do the stiffness prediction. These stiffness profiles were most successful to predict strength, and of course crack you can only predict if you have a 3D description of the continuum, where you have the full stress tensor and check, okay, what criterion could I use to predict strength? And another thing, obviously, if you include information about the eigenfrequency, these correlations in the models get much better as well. But that's kind of a no-brainer. The more information, better prediction. The vision is, again, to summarize here, one day to increase this modeling in speed and have it in the sawmill live to look at different variants of cutting and predict, as I say, the target use of a specific board even one day. That's the dream, at least. A little bit about LTU Skellefteå now, where I work. All my work is also part of a big initiative, an industry initiative called City Wood. We entertain currently 2 different scanners, one medical scanner, the old one, and a very new one, 2 years old now from Microtech, and to the right here, an industrial CT scanner that can operate at sawmilling speeds as well, and has an even higher resolution that I worked with. It's at 0.3 times 0.3 times 0.3 millimeters. We can analyze in situ wood at an elevated temperature of 250 in one of the chambers, and at -60 also to observe freezing phenomena in wood. So we do that while scanning. And we are currently building or designing a combustion chamber as well, where we will be able to study the burning of wood and CT scan at the same time. And I would like to develop some models for that in the future. Thank you.
Thank you, Johannes, for a very nice presentation. And now I would like the guys sitting here and then at the same time leave the scene to Andreas Weidenhille to summarize the project. Happy for that.
Yeah, thank you, Olof. So we are coming to the end of our presentation, and we'll end with a short question and answer session. But before that, I would like to summarize our findings a bit more. Just continue with some very basic takeaway messages. I'm very happy that I have been part of this project. It was a great cooperation, and for me personally, I think I learned really a lot and got to know some very nice people. Thank you for that. Our project READiStrength was a lot of testing and a lot of modeling, and what we can say is we wanted to predict strength, board strength based on log scanning, and that's something that works. We can really do that. It absolutely makes sense. Obviously, it works best with the best data, so that's log CT scanning, but it also works quite well with X-ray scanning. You can even squeeze out some information from 3D scanning, from outer shape scanning, but as you saw, the correlations are a bit shaky. Thanks to the explanations of Rune, we can also say currently the standardization does support log strength grading, log pre-grading if you know how to do it, if you do it correctly. So we can actually start trying this out in sawmills in actual production. We have expressed the hope that this kind of data that we are using and the models we are using here can benefit both the forest enterprises and also the sawmills, so that we can grow together in this value chain. And especially what Johannes told us at the end is, okay, there's even more that we can do. So partly it only depends on computing power, so that we have actually the speed and the power to do the calculations, so that we look into the future and say, okay, and as computing power increases, we can get even better predictions and even better models. And with this, I thank you, and we, please, the team, come over here to the place so that we can continue with some questions.
Just to see if there are any questions for my group, my beautiful team. Yes, a question.
Hello, Dan Ridley, Ellis, Edinburgh, AP University. Thank you for the work that you've done and a pretty clear explanation of something that's hard to talk about. On that theme, I can't really frame a question, so what I'm going to do is throw two thoughts at you and see if you can respond. The first thought that I have is we're assuming that when we have a correlation between knots and strength, that is because knots influence strength. And it could be because knots are affected by something in the growth and strength is affected by something in the growth, and they're not directly related, and all this work pushing towards more sophisticated models won't actually get us where we want to be. That's one thought that I think about. And then the other thought is that very same work has shown us how much variation there is in a piece. And if we do a strength test, well, that doesn't actually tell us the strength. That tells us the strength that we had on that day when we did that strength test. And if the board was 1 millimeter down or the other way up, we would have got totally different values. So that's the other part of the thought that I'm throwing at you is, seeing as we don't have access to parallel universes yet, what is our benchmark? What are we trying to achieve when we don't know the truth?
Is there anyone that would like to comment on that, or?
I would say at least then I try. I have a microphone. Yeah, no, so that's completely true. So the first thing that we actually already came to that point, because when you're using CT scanning, you're obviously able to put a board in there and do some predictions for that particular position of the board in the log. So you can, but at that stage you only can do that on a green board. So you still have to wait until it's dry, or you have already to predict it when it's dry. So in a previous project a couple of years ago, when we started with the CT scanning, we kind of worked around that, and it's rather Magnus and colleagues of his for their PhDs, that they said, okay, we work with probabilities and we work with means on certain position of the board positioning in the log. So that will bring you down in the position of the individual board, but there's a safety, say, margin in there. So, but I'm not as deep into board grading and strength grading, so the question really is how to fit that then with the regulations for strength grading. It's just the input data that can be delivered, say, before sawing.
I find it very interesting, your comments about parallel universes, because I have many times thought strength as a property in timber is a bit like quantum mechanics, quantum behavior. We don't know, we will never know exactly, but we can make probabilistic, in the end, predictions. But to come back to because you said a little bit about modeling, more advanced modeling, will it lead us anywhere? Well, at least we can push in a little bit of our mechanical understanding of the material, which is currently not being used in the grading industry. And we can make meaningful predictions to say, for example, well, probably this board with this certain arrangement of knots should not be used in bending. It should probably be used in compression instead, or in shear, to reduce the risk of a crack. But I agree with you, we will never be able to predict by a mechanical model it will fail now, at this instant, at this load. I agree.
And then you asked what we want to achieve when we can't get the truth. Basically, we want to achieve something that is good enough, something that we can trust when we use it together with the safety factors that we have in the structural work. And as you say, you only have the strength in a very small point, and you can never replicate it. And the good thing with that is that you can never redo it and say we were wrong. So.
Any more questions?
So you started off by grading the log, and then once the boards were in the mill, you were grading the individual boards. Now, coming from a CLT manufacturer, I was thinking, hey, what if we would then scan the whole CLT panel? Well, to squeeze the whole CLT panel through the CT scan, we don't have such a large CT scanner. Maybe in the university for veterinary medicine. No, but you would be able to actually have a glulam beam, the ready glulam beam, go through the CT scanner. Did you look into this option as well, to have this as some kind of a, maybe as a final quality production control, or just as an idea of what strength I have now in my final product?
I think the problem is cost. To have a second CT scanner somewhere to also scan the beam is quite costly. But I think what would be interesting is to combine it with what the team about regrading wood told us. Looking at old planks from buildings that have been demolished, we don't know what's inside. Could you use the CT scanner to regrade that wood?
And might I add also that maybe with these traceability functions that you can actually retrieve some of the information from earlier stages at production as well. And when you make your glulam beam, maybe you have more information available from the log and so on. So you don't need to scan it again, maybe.
And what we should probably also pinpoint here is a problem currently is that the data is not integrated in the sawmill.
Yeah.
You gather this data in the beginning and then you throw it away. You do it currently like this, that you look into the log and you position it a little bit to get the best yield or whatever, and then the data is gone. But there is so many measurements that could be taken along the way which should be integrated together to get a even better prediction if you can follow the product through the line. That is the dream. But I think the value of data is currently not realized in the snow milling industry.
I wouldn't just say that, but say it's a very interesting approach, say for manufacturers following down the production line to a final product or the final product. For us coming from the forestry side, so I'm also a colleague of Udo Sauter, the idea in that project was really to know as early in the production, as in the value chain, what is possible with a raw material which is delivered from the forest. And if you looked at Magnus, the last slides with the R-square whisker plots, you could already question and say, okay, with board scanning, say the models are already that good, and with the scanners we can't achieve better than that. So, but for us it was very interesting to see that, say, at least for our Central European models, we don't need to cut up the log to have such good predictions, but by combining, say, clever technologies, we can already decide in advance what to do with that. And I think then the integration of the information in the sawmill, that should be improved then to give, say, CLT manufacturer then the information to maybe better build, say, design the trusses or whatever you glue, and then be more picky on, say, and differentiate on your raw lamellars. So how you use these with the knowledge coming then from the sawing process.
Yeah. Okay, you want to add to that? Okay, so I might also add that definitely the idea was, of course, integration, as has been voiced by my colleagues already. And of course, you with your product, of course, you're interested, and that's something that I value a lot. Also to integrate the final stage, and of course we want to get there, but I think it was just a bit too much for this one project. So when you mentioned that, I was thinking, okay, maybe a follow-up would be very nice, because there's always more integration to be achieved, and it would be good to see how far we can go there. And of course, what you voiced to do some scans on maybe full beams might be an interesting kind of validation for different models that we have seen yesterday, for example, because we have seen some quite advanced glulam modeling yesterday, also by our colleagues from the Technical University of Vienna, for example. So there's different kinds of predictions that are already available, and it would be very interesting to get to more integration and perhaps different approaches to validation in this way. So I think that maybe CT scanning might also play a part in that.
Thank you.
Mika, can we afford one more question?
Yes. At his hand. Oh, Karin would like to know something. about your question about glulam beams. We have a lot of scanned glulam beams. And we have had them outdoors since 2008. So now we're looking for money to evaluate them.
And then we can apply your models.
Björn Kjellander, I think there are two issues with READiStrength. First of all, the early decision in the sawmill and to increase the yield of both in volume and value. That is, I think, the most nice thing for the sawmill. But we have another issue, and that is the ever-lasting question about new financing of research. And we have another possibility here that you have briefly mentioned, and that is to get away from these silly 5% fractiles and instead actually state this piece of wood has this strength. We saw very early the strength levels of the planks from Sävås sawmill. And why not use these systems to stop producing C24 and throw away a few pieces and actually produce C40 instead?
Well, the question why we're stuck to producing C24 is that the builders, they have always used C24, and they tend to continue with that because no one's producing the higher strength, and no one's producing the higher strength because there is no one asking for it. And so this is many steps that starts at the consultant that usually prescribes C24 because that's what he always did. So there are many steps involved, and it has actually nothing to do with grading in different parts of the process. At the moment we can grade the boards, and we get a much higher yield of C40 than anyone is asking for. So the production is not the problem, there is the consumers.
May I just make a remark adding to that, especially what Franca expressed. The vision is, at least from a Middle European point of view, to start the differentiation quality-wise of logs already on the stand level. And this means we have to fulfill the task to let the data and the information flow back to the forest owners to have this chance. And there are options. We are, for example, working on a solution for traceability individual logs from the forest stand to the sawmill and backwards. So there are chances to do so, despite we know that we will not see a CT in the forest strands. So this is just an adding remark to this whole story. So we are starting already at the resource point.
All right, and thank you. I need to stop it now. Interesting discussion. When we could continue that definitely for another hour. But there are some online participants here as well. So I suppose that when we have announced about the schedule, that we will stop at this point. So I thank you, Olaf. Thanks to the whole team. Thank you.